Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 27th video lecture. And today we want to prove about 5 theorems having to do with uniformly convergence, some things that would force uniform convergence of a sequence of functions to occur. And we also want to get a big fact having to do with if a function, sequence of functions converge uniformly continuous, and each one of the functions involved in the sequence is continuous, then the function it converges to, the limit function, will be continuous. That's what we'll end with, I believe, during this lecture. We'll need a big theorem to get to that lecture as well, get to that theorem. And we will prove that today. Well, let's go ahead and get started. Our first theorem is the following. It says, suppose that the limit as n goes to infinity of f sub n of x equals to f of x, and that's for each x in some set E. And we're thinking here this means pointwise convergence. What we're going to do is we're going to put m sub n equal to the sup of the absolute value of f sub n of x minus f of x. Remember, this is in complex numbers here. It's absolute values. Then f sub n converges to f uniformly on E if and only if m sub n as a sequence of functions converge to 0 as n goes to infinity. Okay, we want to prove this. All right, so we're going to suppose the given part of the statement. That is, suppose that the sequence of f sub n converge they converge pointwise to f, okay? That is, we're supposing that the limit as n goes to infinity of f sub n of x equals to f of x. That's for each x in E. We're going to put m sub n equal to the sup of f sub n of x minus f of x inside absolute values. Now, what we do is we think of n being fixed, for fixed n. This is what we're defining. And this is the sup over all x element of E. So here the x's are kind of running, and we're finding the biggest difference. Now, this is an if and only if statement, so we have 2 directions to prove. Here in this first direction, we'll suppose that the f sub n converge uniformly to f on E. And what we want to do is we want to show that the limit as n goes to infinity of m sub n equals to 0. So we're going to let epsilon be greater than 0 be given. Okay. We need an n that's a natural number. Such that, so I'm just using the definition of what it means for a limit of real numbers to converge, limit of the sequence of real numbers. Okay, such that m sub n minus 0, this will converge to 0, will be less than epsilon, and that's for all n bigger than or equal to this big N. That's our natural number. So what we want, absolute value of m sub n here, minus 0, that's just m sub n. We want that to be less than epsilon. Well, now notice that what n sub n is defined to be, so that means we want the absolute value of the sup of the absolute value of m of f sub n of x, this is all x is in e, minus f of x. We want that to be less than epsilon. Oops, this needs another absolute value. Well, here, this is just going to be the sup. So we want the absolute value of this non-negative number here. We want the sup is x goes all over e's of the absolute value of f sub n of x minus f of x. We want that to be less than epsilon. Okay? Well, how are we going to get that? Well, we're going to get that through the uniform convergence. So, since f sub n is a sequence of functions, converge, and I'm going to say uniformly. Remember, what I'm looking for is that n. Uniform convergence is going to give you that n. Since f sub n, so the sequence of functions, converge uniformly to f, then there exists an n that is a natural number such that for all n bigger than or equal to this big N, the absolute value of f sub n of x minus f of x will be less than, well, I'll say epsilon over 2, and that's for all n greater than or equal to big N. Okay? And for all x element of E. Okay? Thus, I guess it's what we want, that the sup over all x of E of f sub n of x minus f of x, that's going to be less than or equal to epsilon over 2, which is going to be less than epsilon. And that's what we wanted to show. So it's a conclusionary part of this part here. So the limit as n goes to infinity of m sub n, that will equal to 0. Now we have to show the other direction. So suppose the limit as n goes to infinity of m sub n equals to 0. And here we want to show that the sequence converges uniformly there. So we let epsilon be greater than 0 be given. Okay. We need an integer, really it's a natural number. Say big N, such that for all n bigger than or equal to big N, the absolute value of f sub n of x minus f of x will be less than or equal to epsilon, and that's for all n, for all x element of E. That's what we want to show. That's the definition, uniformly convergent. Now, since the limit as n goes to infinity of m sub n, that's what we're assuming equals to 0, then there exists a natural number m such that for all n bigger than or equal to n, m sub n minus 0 inside absolute values will be less than epsilon. Which implies that the absolute value of m sub n is going to be less than epsilon, which implies that the absolute value of the sup over all x element b of the absolute value of f sub n of x minus f of x, that's going to be less than epsilon, which implies that the sup over x element b of f sub n of x minus f of x is going to be, inside f of values, less than epsilon, and that implies that the absolute value of f sub n of x minus f of x is less than or equal to epsilon. Okay, and that's true for all n, and this is true for all n bigger than that big N and for all x element of E. And so that's what it takes for the f sub n to converge uniformly. That's what I'll write at the conclusion of this proof. Thus, the sequence of f sub n converge uniformly to f on E. And that is okay. Next theorem I'm going to write up has to do with a summing up of a sequence of functions and something about converging uniformly to the sum function. So here, we're going to assume, to suppose, that f sub n is a sequence of functions defined on E and suppose f sub n of x is less than or equal to some m sub n for all x element of E and for n equal to 1 or 0 even if you start there, 2, 3, forever. Now this m of n is just some real number that bounds the absolute value of f sub n of x. It's not the same m of n that we had in the previous theorem, okay? To conclude this statement, then f of x, f sub k equal to the sum, as n runs from 1 to infinity, of n runs from 1 to k, of f sub n converges uniformly on E if the sum of the m sub n's converge. And here this would be n running from 1 to infinity. Excuse me. All right, we're going to prove this. So we're going to suppose that the sum of the m sub n's converges. We let epsilon be greater than 0 be given. Since the sum of the m sub n's converge, then there exists a natural number big N, such that for all n bigger than or equal to m, bigger than or equal to big N, this sum, well, the sum is, I'll say k runs from m up to n, that's the value of this sum, of m sub k will be less than epsilon. And this is by the Cosy criterion for convergence of a series, which we learned about in chapter 3 and did just several lectures ago. Okay, well, when we look at that absolute value of that sum, we should notice that the m sub i's, the m sub whatever's involved in this, they're going to be greater than or equal to 0. Okay? Since that happens, we have that for all n greater than or equal to m greater than or equal to big N, the sum as I runs from m to n, I called it k before. Well, we'll change it to I. I running from m sub I will be less than epsilon. So I just, beforehand had k's, I just changed them to i's. No big deal. Okay. Thus, for all n bigger than or equal to m bigger than or equal to this big N, the absolute value of the sum, so this is what I want to look at, is I runs from m to n of f sub n, f sub I of x. Well, if we bring the absolute values inside the sum, so it makes it smaller, it makes it bigger. I miswrote these. Okay, that's what we have. But this guy is less than or equal to, I'm going to replace the absolute values of the f sub i's by the m sub i's. Well, it's just m sub I, not the f sub value of it. As I runs from m to n. Okay, and we know that that's less than epsilon. Okay, or if you want, you can say less than or equal to epsilon. So, for all n bigger than or equal to, well, I'll just write this way. For all n and m bigger than or equal to big N, the sum as I runs from 1 to n of f sub I minus the sum as I runs from 1 to n of f sub m, f sub I should say. So I runs from 1 to m on the second one. Okay? That guy is equal to, what I'll rewrite it as is an absolute value of the sum. So this difference, it's going to be I running from the minimum between m and n up to the maximum between m and n of f sub I. And I should finish it down there. I'm sorry. And that's going to be, I think I got one right here. That's going to be less than or equal to epsilon, our previous word here. Okay? So we got that less than epsilon. And so what we can use is a theorem we've already proven last time. It's that Cosy criterion for uniform convergence. Of a sequence of functions. We have, here's where I'll write it, the sequence of big F sub n's, that's what I'll call it, n running from 1 to infinity, which really is equal to the sum, maybe as I runs from 1 to n of little f sub I, which was the sequence that we were working with. Here n runs from 1 to infinity. Converges uniformly on E. And that is this proof. Okay, well next we want to prove kind of a very technical statement that has us being able to change the order of taking some limits. And again involves uniform convergence. Namely, we have this theorem. Suppose the sequence of f sub n's, matrix of functions converge uniformly to F on E. Here I'll say on a set E. We're going to do this very abstractly in a metric space. So E is some subset of a metric space. Let X be a limit point of E, and suppose the limit as t goes to x of f sub n of t equals to a sub n, and that's true for all n, n to 1, 2, 3, forever. Then the sequence of the a sub n's converges to the limit as t goes to x of f of t I should say converges and sorry, I made a mistake. The limit as t goes to x of f of t, what it's going to converge to is the limit as n goes to infinity of a sub n. And I've got just enough room, I want to write this down here. What this theorem is saying, that is, so this is a parenthetical expression, the limit as t goes to x, okay, of the limit as n goes to infinity. So here I'm looking at this part, of the f sub n of x, because that's what f of x is. Or here I should say, maybe t. I should write t. Equals, this part is the limit as n goes to infinity, and then the a sub n is what is the limit as t goes to x of f sub n of t. And so we're interchanging those limits. We're able to do that by this theorem. Okay, we want to prove that. It's a little bit of a lengthy proof. Okay, so we're going to suppose that f sub n converges uniformly to F on E in a metric space. So E's in a metric space. And we're going to let little x, that's not the metric space, okay, be a point, be a limit point. Of E, and suppose that the limit as t goes to x of f sub n of t equals to some quantity a sub n. Okay? What we want to do is we want to show that the limit as n goes to infinity of a sub n equals to it's f, well, we want to show that it's equal to the limit as t goes to x of f of t. That's what we want to show. that's what we want to show. All right, so we're going to start off by letting epsilon be greater than 0 be given. We'll show these two limits are the same. Okay, since the f sub n's converge uniformly to f, that's on E, then we're going to get an integer, n, so there exists an n, there exists this n, an integer, such that for all n and m bigger than or equal to n, and t element of E, that is that f sub n of t minus f sub m of t is going to be less than or equal to epsilon. That's by that Cosy criterion for the uniform convergence. And so as a claim, the limit as t goes to x of f sub n of t minus f sub m of t, this guy is going to be equal to a sub n minus a sub m inside absolute values. So we're going to prove this claim. Proof of claim. So we're going to prove that these are equal. So we let, don't let this bother. I'm calling epsilon 1 to be different than epsilon we be given. Let epsilon 1 be greater than 0 be given. We need a, I'll call it delta sub 1. We're talking about a limit, okay? Delta sub 1, limit of here functions, greater than 0. Such that for all t in E, remember E is part of a metric space, with, we're talking about a limit of a function, so it's 0 less than the metric, okay, I'll call it D, in our metric space, of t and x. When that's less than delta sub 1, then the absolute value of f sub n of t minus f sub m of t minus the absolute value of a sub n minus a sub m, that will be less than epsilon sub 1. Okay, that's what we're looking for. We need this delta sub 1. It's epsilon sub 1 right here. You can see it. Okay. Well, let's make this observation. Note that the absolute value of f sub n of t minus f sub n of t minus the a sub n minus the a sub m inside absolute values. That's going to be less than, or it can be shown. that this is less than or equal to the absolute value of f sub n of t minus f sub m of t minus a sub n plus a sub m. Okay? And that is going to be rewritten as the absolute value of, well, I'll rearrange these. So this is the absolute value of f sub n of t minus a sub n, and then I'll rewrite this as plus a sub m minus f sub m of t, and then that's less than or equal to, using the triangle inequality, f sub n of t minus a sub n plus, here, this can be rewritten, it's a sub m minus f sub m, but I can pull out a minus, and that makes it f sub m of t minus a sub m. That's the same thing. Now, let's remember, since the limit as t goes to x of f sub n of t equals to a sub n, then there exists a delta sub 2 greater than 0 such that for all t element of e with 0 being less than delta of t and x, d of t of x, that metric was less than delta sub 2, then this got to be made real small. Then the absolute value of f sub n of t minus a sub n will be less than, let's say, epsilon over 2. Similarly, since the limit as t goes to x of f sub m of t equals to a sub m, there exists a delta sub 3 greater than 0 such that for all t element of E with 0 being less than the metric between t and x being less than delta sub 3, then the absolute value of f sub m of t minus a sub m will be less than epsilon over 2. Then we let, remember we're looking for a delta sub 1, so we let delta sub 1 equal to the minimum between these two deltas. That is delta sub 2 and delta sub 3. Then, what we get is for all t element of E with 0 less than delta of t x less than delta sub 1, we have, let me write over here, So we have that the absolute value of f sub n of t minus f sub m of t minus the absolute value of a sub n minus a sub m will be less than or equal to. So this is something we already had. It was f sub n of t minus a sub n plus the absolute value of f sub m of t minus a sub m, which is going to be less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So that ends the proof of the claim. I'll write this down. So the limit as t goes to x, the absolute value of f sub n of t minus f sub m of t will be equal to the absolute value of a sub n minus a sub m. That ends the proof of claim. Okay. Now, since the absolute value of f sub n of t minus f sub m of t is going to be less than or equal to epsilon, and that's true for all n and m bigger than or equal to the big N that we had, and for all t element of E, this was true because of the uniformly convergence of the sequence of the f sub n's. Then the limit as n goes to infinity, as t goes to x of f sub n of t minus f sub n of t will be less than or equal to epsilon, and that's for all n and m greater than or equal to n. Okay. So that says that a sub n minus a sub m will be less than or equal to epsilon, and that's true for all n and m greater than or equal to n. Thus, the sequence of a sub n's forms a Cosy sequence in, we're talking about in C. And therefore, converges to a number, say A. Let's call that number. Okay, we now want to show that the limit as t goes goes to x of f of t equals to a. So to show this limit, we're going to use the definition, a delta, I'll say sub 4, we've been given epsilon already, greater than 0, such that for all t element of E with 0 being less than the distance between t and x, being less than delta sub 4, then the absolute value of f of t minus a will be less than the epsilon that's been given to us. So let's observe that f of t minus f of a, minus a, that's equal to the absolute value of f of t minus f sub n of t minus f sub, I think it should be plus f sub n of t, minus a sub n plus a sub n minus a. And that's going to be less than or equal to, so I'm splitting this up into 3 absolute value sums. So f sub t minus f sub n of t plus the absolute value of f sub n of t minus a sub n and plus a sub n minus a. We need to make sure that each one of those absolute values is real small so that when we sum them up, it's less than epsilon. Okay, well, since f sub n converge uniformly to f, there exists a natural number n sub 1 such that for all n bigger than or equal to n sub 1, f sub t minus f sub n of t will be less than epsilon, less than or equal to epsilon over 3, and that's true for all t element of E. Since the sequence of a sub n's converge to A, there exists a natural number we call it n sub 2, such that for all n bigger than n sub 2, the absolute value of a sub n minus a will be less than or equal to epsilon of 3. Less than epsilon of 3. Okay? That's what we have. Now, the next thing we need to do is to establish that since the limit as t goes to x, f sub n of t equals to a sub n, there exists a delta support greater than 0, such that for all t element of E with 0 less than delta, the distance between t and x being less than delta support, then the absolute value of f sub n of t minus a sub n will be less than or equal to epsilon over 3. Okay? So, here's what we have. For all t, element B, with 0 being less than the distance between t and x being less than delta over 4, we have. So I'm looking at the absolute value of f of t minus a. I'm going to rewrite that as I had before. I had f sub n's and a sub n's involved, but the little n's. But now I'm going to use this big N. Okay. And I've made a mistake. Well, an omission. This is going to be equal to f of t minus f sub big N of t plus f sub big N of t. And then here we're going to have minus a sub n plus a sub n minus a. Which is less than or equal to f of t minus big F sub n of t plus the absolute value of f sub n of t minus a sub big N of t, and then plus the absolute value of a sub n. This should be big N's here. Big N's. It's not a TU, just a sub n. Minus a. Okay. Where, I forgot to say this, but n is really equal to the maximum of the n sub 1 and n sub 2 that we used earlier. Okay? So we have found a particular term, f sub big N, in our sequence, such that we're getting this inequality. We will get this for any particular f sub whatever. But for that particular n, by our previous work, that's going to be less than or equal to epsilon of 3 plus epsilon of 3 plus epsilon of 3, which equals to epsilon. Okay? And so that proves what we're going to see. Okay, I'd like to state and prove a very short theorem, a big, it's an important theorem. And let's go to do so and conclude with this. If f sub n is a sequence of continuous functions on E, and f sub n converges uniformly to f, then f is continuous on E. Before we go to prove this, what I want to tell you is this wasn't true for pointwise convergence. So you could have a sequence of functions f sub n that were all continuous. But what they converged to point-wise wasn't continuous. We saw an example of that. But here, if this statement is saying that if your sequence of functions are continuous and they converge uniformly, what they converge to has to be continuous as well. We're going to prove this statement and then call it quits for this lecture. By the way, before I start to prove, we're thinking E is a subset of X, which is a metric. That's our saying about our domain space. So here's the proof. We're going to let f sub n be a sequence of functions that are continuous on E and converge uniformly to F on E. Okay. We want to show that F is continuous on E, and we're going to do this by two cases, okay? So case one, we'll let X be an element of E, and so our job to show that F is continuous on E is that if you give me any X in E, we want to show F is continuous at X Okay. So, by previous fact, if we look at case one, suppose X is not a limit point of E. Then this happened in analysis one. What that shows F is automatic continuous at X. That's from a fact from analysis one. And then case two is suppose X is a limit point of E. Well, here's what we see. Since f sub n is continuous, on E, and X is an element of E, then the limit as t goes to X of f sub n of t, that's going to equal to f of x, okay, due to the continuity and t and x being a limit point of E. So by the previous theorem, I made a mistake here. Oh gosh. Sorry. Okay. But my mistake here is it doesn't converge to f of x, it converges to f sub n of x. Okay? Here's the continuity of f sub n. I wasn't paying enough attention. I'm sorry. So, as I was saying, by the previous theorem, the limit as t goes to x of f of t will be equal to the limit as n goes to infinity of f sub n of x, and since this converges, it converges to f of x, and that shows f is continuous at x. And so in all cases, f is continuous on E. And that's what we wanted to show. That's enough for today. Thank you very much.